Okay, welcome friends. Here we are discussing how to solve linear differential equation. For that, I am considering general linear differential equation dny by dxn plus a1 into dn minus 1 y by dxn minus 1 plus a2 into dn minus 2 by dxn minus 2 plus so on plus n into y is equal to x. This is our general linear differential equation. Moreover, its order is n and degree is 1. Now it is better for our convenience, I'll put d by dx as this capital D. Then we can write here d2 by dx2 is d square, and in this way I am using this for our convenience to convert this equation in terms of this is dny plus a1 into dn minus 1y plus so on plus n into y equal to this x, where these a1 a2 a3 so on an all these are the constant. A1 a2 an are constant. Now this is our linear differential equation with constant variables. A1 a2 a3 these are the constants. Now here from this equation I will take y common. You can write d raised to n plus dn minus 1 a1 into plus 1 plus an to y equal to x. Now this is just like a polynomial in terms of d. Therefore I will write this is a polynomial of d, or I will say this is a function of d into y equal to x. Means whole this equation 1 I can represent in terms of some short form as f of d into y equal to x. Now what is this f of d? F of d is a function of d, and this f of d is nothing but d raised to n plus a1 into d raised to n minus 1 plus on an into y equal to x, and this f of d is only this coefficient of y. This is also called linear differential equation. Means this equation 1 we can write in short form as f of d into y equal to x. Now our aim is to solve this differential equation. Now how to solve? In our last example, from this last example we are knowing that this solution is, or I will say that this is the general solution is y equal to cf plus pi. Cf is called complementary function and this pi is called particular integral. This is a complementary function and this is a particular integral. Now again we are knowing that this complementary function is the solution of this, either 1 or 2. This complementary function is solution of this equation. Moreover, this is for homogeneous part, means complementary function is the solution for f of d into y is equal to 0 part. Again from this you can write here f of d into 0, this y solution, and this is over 0. Therefore I am taking this f of d equal to 0, and from this equation we can find out this cf. Now here this is our general solution, and general solution we are getting cf plus pi. Now our aim is to find out cf as well as to find out pi. Now if we are concentrating on cf, we are knowing that already from last example also we knew that this cf is a solution of homogeneous part of this equation 2, linear equation. Now I am taking this homogeneous, and from this we are getting f of d equal to 0. Let us, I will try to proceed this. What is f of d? This is our polynomials in terms of d. This is our polynomial. F of d is nothing but this is our polynomial in terms of d. I will rewrite this polynomial as d raised to n plus a1 into d raised to n minus 1 plus so on plus an equal to 0. This is a polynomial in terms of d of degree n. Therefore, surely this polynomial having n roots, or I can write factors as d minus m1 into d minus m2, so on, d minus mn equal to 0. Because this is polynomial of degree n, therefore we can write here these are having m roots. If this equation having m root, that means this solution I can write in this way: d minus m1 into y equal to 0, d minus m2 into y equal to 0, and so on, d minus mn into y equal to 0. Actually, our aim is to find out this CF. From this, for that, I am using this condition of homogeneous equation, and I am finding here roots of this. Now here, I will concentrate for this first equation, and same logic we will apply to remaining equation. Now here, from this, we are getting d minus m1 into y equal to 0. That means I will try to write this equation in this way: d into y, I am multiplying this y to this bracket, minus m1y is equal to 0. What is dy? D means our derivative. This d is nothing but d by dx. I will write here d means this is a dy by dx minus m1y equal to 0. Now this is our linear differential equation of first order. To solve this equation, we can find out integrating factor and so on. From that we are getting our solution. And here from this we are getting solution as, I will write directly y equal to something constant. I will take c1 into e raised to m1x. How we are getting this? I will solve this here. For this equation, integrating factor is e raised to power minus m1x. Then solution is y into integrating factor, which is equal to this right hand side is 0, therefore this part is integration q into 0, means we are getting this 0 plus this constant I am taking c1, and from that we are getting y is equal to c1 into e raised to m1x. Therefore I am taking this step directly, y equal to c1 into e raised to m1x. Now we are getting this is solution for this term. We are having now here such a n terms. This term is also there, this term is also there. Therefore I will write all possible solutions in this way. Yes, from this we are getting solution as y equal to c2 into e raised to m2x. Again I will write here last y equal to cn into e raised to mnx. All these are the solutions for this, and we are getting these solutions. Now if I will take all these roots, now I will take three conditions here depending on these roots of this equation. I will take three conditions. Suppose this equation having roots, number first case, real and distinct. All these roots are real and distinct. Then we can write our CF as, this is combination of all these roots. All these roots are here. This is c1 into e raised to m1x plus c2 into e raised to m2x plus so on, plus cn into e raised to m1x. And this is your root for the case if our these roots m1, m2, m3, all these are the roots for this equation. If all these roots are real and distinct, then we can write our solution in this way: c1 into e raised to m1x plus c2 into e raised to m2x plus c3 into e raised to mnx. This nth degree polynomial having n roots, and moreover these are the real and distinct, then we can write our solution in this way. Now I will take second case. If roots are real and repeated, if roots are real and repeated, then what will happen? Means here this is the case. Suppose m1 and this m2 both are here. I will take this is suppose first m1 equal to m2. These are the two roots. Then what will happen? If m1 equal to m2, then we are getting this m1 equal to m2. Then in this case, what will be our CF? Here I will write this equation and this equation again having factors, this d into m1, d into m2, and so on. All these factors are there, and I will take first of all suppose these two terms, because having roots are same, as d minus m1 into d minus m2 into y equal to 0. And again we are knowing that m1 equal to m2, this is case. Here I will put d minus m2 into y equal to suppose u. Then this above equation we can write d minus m1 into u, this term is u, is equal to 0. Now this becomes again linear differential equation of first order and first degree. Therefore we are getting directly solution of this u equal to e raised to m1x. This u equal to e raised to m1x. That means here I will put value of u at this point, this u. Therefore above equation we can write d minus this m2. I can write m2 or m1, doesn't matter because both are same. This d into m1 into y is equal to u. What is u? E raised to m1x. Now this equation is also linear differential equation. We can solve this linear differential equation as this equation. I will rewrite first of all in our proper form, dy by dx, because this capital D means dy by dx, minus m1 into y is equal to e raised to power m1x. Now what is integrating factor? E raised to minus m1x. Therefore its solution is y into integrating factor e raised to minus m1x, which is equal to integration e raised to this m1x, this part I am taking here, into integrating factor e raised to minus m1x into dx plus something constant I will write here. I will take this constant, suppose I will take c. This is equal to e raised to m1x and e raised to minus m1x get cancelled. We are getting only dx plus this c, means we are getting x plus c. We are getting this is x plus c, this is y into e raised to minus m1x. Hence this y equal to just put here. We are getting this solution as, I will take something constant here, this constant c1 into e raised to m1x, this constant into e raised to m1x, and here I will write this constant c1. Now here is constant c1, here is again constant c1, that's why I will write here this constant c2. Okay, now this is c1 and this is c2. We are getting this is c1 and this another constant c2. Now we are getting this as c1x plus c2 into e raised to m1x, and this is a condition to find out if roots are repeated. If m1 root is repeating, then we are getting this solution of CF in this way, c1x plus c2 e raised to m1x. If suppose this case happens, m1 equal to m2 equal to m3, repeated 3 times, then what will be our CF? We will generalize this, c1 x square plus c2x plus c3 into e raised to m1x. In this way we can write our CF if roots are repeated. Remember this, if roots are repeated, then we can write our CF in this way, c1 into x square plus c2x plus c3 into e raised to m1x. Now I will check third case. Third case is roots are complex. If suppose roots are complex, then what will happen? Because we are knowing that any quadratic equation having two types of root, either distinct or repeated, distinct and real, repeated and real, and otherwise complex. If suppose I will take roots are complex, suppose m1 equal to alpha plus I beta, then surely this m2 there exists m2 alpha minus I beta. Two roots are there, alpha is real part and beta is imaginary part. Then again in this case what will happen for our CF? Means again I will recall here, this is our equation. This equation having m1, m2, m3, all these are the roots. First case, all roots are distinct and real. Second case, these roots, suppose I am taking only first two roots are repeated and remaining are distinct. Or again, we have gone through this case also. Suppose first three roots are repeated, then what will be CF? Now third case, suppose this m1 and m2 both are complex roots, then what will happen? This alpha is real part and beta is imaginary part. This real part is alpha, imaginary part is beta. Now again, I will try to find out the CF in this way. We are knowing that if roots are distinct, then our CF is, if roots are real and distinct, our CF is C1 into e raised to m1x plus C2 into e raised to m2x. I will take only two roots and then we will try to find out here e raised to m1x and e raised to m2x. Now here roots are complex here, then I will, and complex and moreover these are the distinct roots. That's why I will write this property C1 into e raised to m1x plus C2 into e raised to m2x. But m1 is complex, e raised to alpha plus I beta into x plus C2 into e raised to alpha minus I beta into x. This is nothing but C1 into e raised to alpha x into e raised to I beta x. I am multiplying by x and then separating this, plus C2 into e raised to alpha x into e raised to minus I beta x. Now here this e raised to alpha is common. I will take outside e raised to alpha x into bracket. Remaining term is C1 into e raised to I beta x plus C2 into e raised to minus I beta x. Again further I will try to expand this, and we are knowing that Euler's theorem. Euler's theorem is e raised to I theta equal to cos theta plus I into sin theta. This is by Euler's formula. I will write here this Euler's formula. By using this Euler's formula, e raised to power alpha x into C1 into e raised to I beta x. Therefore, this is equal to cos of beta x plus I into sin of beta x plus C2 into cos of beta x minus I into sin of beta x. I am using here also. Now I will collect real and imaginary part. Then we get here C1 multiplied by this term, C2 multiplied by this term. Therefore, I will write e raised to alpha x into the C1 into this term, C2 into this term. This is our real part. I will write here C1 plus C2 into cos of beta x plus this I is here, minus I is here, sin beta is also common, and I will write here C1 minus C2 into I into sin of beta x. This is your real part, this is your imaginary part. Again here I will write this is your C1 plus C2. C1 and C2 both are constant. C1 plus C2 is again another constant. C1 minus C2 is constant and I is again constant. Therefore I will write this as e raised to alpha x into A into cos of beta x plus B into sin of beta x, where this alpha is a real part and this beta is imaginary part of m1 equal to alpha plus I beta and m2 equal to alpha minus I beta, and this is our CF. And so we can write easily CF if roots are complex, then our CF is CF equal to e raised to power real part into x, something constant A into cos of this beta, beta means imaginary part, this beta imaginary part, plus B into sin of beta x, this B into sin of beta x. In this way we can find out CF. I will summarize this, what we learned and what is method to find out CF. For CF, number one case first is if roots are real and distinct, if I am taking only m1 and m2 roots, this equation having only m1 and m2 root, then how we are finding the c of c1 into e raised to m1x plus c2 into e raised to m2x. If roots are real and distinct, then our CF is in this way. Again, remember this, I am only taking these two roots are there. If n roots are there, then we can write in addition n. If roots are real and repeated, then our CF is c1 plus c2x into e raised to power m1x. You can write c1x into c2 or c2x into c1, doesn't matter. And third case, if roots are complex, means m1 equal to alpha plus I beta and m2 equal to alpha minus I beta, then our CF is e raised to power real part is alpha into bracket a into cos of imaginary part into x plus b into sine of imaginary part into x. Means if we know roots of this equation, then we can find, if we know roots of this equation, again this is our linear differential equation, and if we know roots of this equation f of d equal to 0, f of d equal to 0, then we can find out CF, and again CF depending on nature of roots of this equation, real, distinct, real and repeated, and complex, and this equation is called auxiliary equation. This equation is called auxiliary equation. Means if we know roots of auxiliary equation, then we can find CF, and this is the method to find out CF. Okay, in coming lecture we will solve problems on this. Okay, thank you.